Okay, hey, what's up? Welcome back. Hopefully everyone had a wonderful break. Let's do some proofs. Prove some stuff. Let's get back to talking about sets. So, if you recall, last time we were proving the following theorem. So we had said, all right, if A is weird less than or equal to sign n, some initial segment of the naturals, that is, if there's an injective function from A to some initial segment of the naturals, then A is finite. So we're going about proving this, and we tried one method. Now I want to talk about the other way to go through and do it, something perhaps maybe more constructive and in some ways more illuminating, though it is, like we talked about last time, a little bit overkill compared to another way of getting there. So we'll talk about it. We'll get there. If you recall, quickly, that a set is finite if it has n elements for some n in the naturals. That is, if there exists a bijection f from A to nn, where nn is the set of m's in the natural numbers, satisfying the predicate m is less than or equal to n, where n is that little subscript. Okay, so these are just like the little chunks of numbers up to n, yeah? So that's how we're counting how many elements a set has, by putting the elements in a bijection with the first n elements for some n, yeah? Cool, okay. So to prove this theorem up here, that says that if, oh wait, did I say this? Yes, this is good. Okay, yes. I think I looked at the theorem before it for a second and second-guessed myself that I had said something wrong. No good. Okay, so to prove this, we're going to prove a quick little lemma. This lemma is hopefully pretty straightforward. Let f from a set A to some initial segment of the naturals be an injective function which is not surjective, then the claim is that there exists an injective function g from A to n minus 1. That is, if you have an injection that is not a surjection, then you could get rid of something, yeah? It is hopefully a relatively straightforward claim. The idea is something like this. You've got, say, like A, maybe this has like A, B, and C in it. And over here, I've got, say, like N5. 1, 2, 3, 4, 5. Here's an injection. This is certainly not a surjection. Yeah? The claim is that we can find an injection to N4 in this case. Do you believe this? Yeah, totally. Totally. All we have to do is reassign the thing that gets mapped to 5 to something smaller than it that doesn't get hit, right? Okay, cool. So to do this, to show this, we'll just basically use exactly that idea. This little lemma, this little fact, will help us prove this guy up here. Okay, so let's do it. Proof. let f from a to n, that initial segment of n natural numbers, be an injection that is not a surjection. Okay, well, there's one really easy case when you have an injection g from a to n minus 1. That would be the case where f never hits little n, yeah? If f of, I'll write it this way, if f of a is not equal to n for all a in a, define g from a to n minus 1 by g of a is iota composed with f of a for iota from, all right, this way, for iota from n, or maybe put it this way here. Actually, let's do this. I won't even bother with that. Here's what I'm going to say. By g of a is f of a. If I really wanted to be correct, what I should say is by iota composed with g of a is f of a for iota from n minus 1 to n, the inclusion iota of x equals x. Yeah? If I want to really be correct about domains and codomains, right? But basically all I'm saying is that make this new function g just be exactly the same as f. Yeah? Okay, cool. So if you can do that, great, you're done. If f of a equals n for some a in a, then since f is not surjective, there exists m in n with m strictly less than n, such that f of, I'll write it this way, b is not equal to m for all b in a. Yeah? So since it's not surjective, if it does hit n, well then there must be something else it doesn't hit. Necessarily that has to be something smaller than n, right? Okay, so define g in the following way. I will make it equal to f of x if f of x is not equal to n, and I will make it equal to m if f of x is equal to n. Notice this is well defined. Since f is injective, there is only one such value b for which, or sorry, since f is injective, there's only one such value a for which f of a is equal to n, right? Okay, so it's literally exactly the same except for the case where you hit n, you get instead now m, something smaller that you didn't hit. Yeah? Cool? Or here's even a nicer way to write this. F of x if x is not equal to a, and m if x is equal to a, where a is that value such that f of a is n. The same thing, right? Okay, cool. So if you like this, since f is an injection, so Not 2 O's and so. 2 O's and 2. So 2 is G. Do you believe this? All I've done is switch one of the values. I've taken it from n to m. It didn't hit m before. Now it does. Doesn't hit n. Okay, cool. You guys are fine with that. I won't write and show it. But, okay. In either case, we are done. That is, in the first case, if f of a is not equal to n for all a and a, then we just use a function g that is exactly the same, yeah, but has a different codomain. If it is true that f of b or f of a is equal to n for some a, then, since it's not surjective, there's some m that we don't hit. So all we do is we replace the value of f of a with m. Yeah? So just switch one thing. Does that make sense? It's exactly the picture we were drawing before where it's like, hey, if you hit the biggest one, well, if it's not a surjection, you could just switch that biggest one to something you didn't hit earlier on, and now you don't hit the biggest one. Easy peasy. Okay, so we'll use this nice fact here that says that, hey, if you've got an injection that's not a surjection, then you can take an injection to something with one fewer element, yeah? And we'll show that if A has an injection to n sub n, some initial segment of the naturals, then A has a bijection to some initial segment of the naturals. Perhaps not the exact same one, but at least some of them, yeah? Okay, so to do this, we will, oh, wrong button. Yeah, here we go. Okay, so to do this, first I'll need to move this annoying string. Okay, so to do this, here's the kind of straightforward way. All right, suppose that A, weird less than or equal to sign, and n, then what this means is that there exists an injection f from A to n. If f is surjective, then this is a bijection, and A is finite. Yeah? That's what it means to be finite. Okay, cool, great. If not, then there is a, or I'll say an injection G from A to n minus 1 by the previous result. Yeah? You agree with this? Perhaps? Okay. Now, repeat. Yeah? That is, or maybe I should say this. That is A weird less than or equal to sign n minus 1. Now, we just continue to repeat this until we eventually get a bijection, yeah? Eventually we get a bijection. I'll call it G from A to n minus m for some m between 0 and n. Or even we could say between 0 and n minus 1. Or we find that, I'll even say that A is weird less than or equal to the empty set, which notice is equal to n 0. Yeah? Yeah? Maybe? Yeah, and it has 0 elements. Certainly in that case it would be finite. If not, eventually you get a bijection, and you also have finiteness. So good to go. What do you think? Yeah? Feeling good about it, or no? Okay. In some ways, this actually perhaps relies on something that I am not proving here, which is that if you have a process that you can repeat until you get your desired result, and there is some stopping point where the process must terminate, right, then eventually you get your desired result. I am to some extent kind of hand-waving that fact. It is something that I guess we should maybe show, that any process which gives you, which either can be repeated or gives you your desired result and must eventually terminate, does indeed give you your desired result, yeah? But hopefully that is at least a relatively intuitive thing, although we should not purely rely on our intuition in mathematics. In this case, I would say that it is fine since this is, it terminates after a finite number of steps. So in some ways, I am only hand-waving away, just rewriting the same thing a lot of times, yeah? Okay. Now, with that in hand, let me ask you a quick question. Here is an easy question that might seem obvious, but ask yourself, can you prove it? Think on it for a minute. If m and n are natural numbers with n not equal to m, can you show that nn is not equal to nm? Actually, let me make that even nicer. I'm sure you can probably say that. Can you show that they are not equinumerous, at least? Yeah? That is, can you show that 1 through n and 1 through m don't have the same number of elements if n is not equal to m? Perhaps it seems incredibly obvious, but can you formally do so now? What do you think? How would you do so? Well, I would say perhaps you should turn your attention back to the thing we just showed. That is, if you have a set that has an injection to nn, then A is finite. Okay, cool. That's great, right? Now, we use this little result that says that if A has an injection to nn, and this is not a surjection, that A has an injection to nn minus 1. Okay, so think to yourself for a moment. If n is not equal to m, then n is less than m, or m is less than n, yeah? Okay. For, not, so we don't have to repeat the exact same argument with just n and m swapped. Let's say, suppose, without loss of generality, which is a fancy mathematician phrase meaning like, hey, it's the exact same argument, you just switch the letter, yeah? That, let's say n is bigger than m, yeah? Okay, cool. Well, if you suppose this, then the inclusion is an injection that is iota from an m to an n. It is not a surjection. Yeah? Do you agree with this? Okay. So you can get down to, an injection from nm to n minus 1. Okay, cool. And so on and so on. Can you show that they are not, in fact, equinumerous? How would you do so? Remember, to show that they're equinumerous, you have to construct a bijection. Yeah? You'd have to somehow show that there exists no bijection between them, right? Okay. So what would you do? Effectively this, yeah. This basically works, right? That is, what we're showing is we're showing that there is an injection to a smaller set. But we know that you can't do this if the sets are the same size, right? Yeah? Okay, perhaps this isn't clear. But I guess what I'm trying to get to is that you have all of the tools and machinery now to prove, albeit in a what feels like overly complicated way, basic facts that you perhaps have taken for granted, right? That sets of numbers with a different number of numbers in them are not the same. It kind of seems like an obvious fact, right? It seems like a very basic thing, but before that, what would you have written as a proof? You would have been like, I don't know, let's look at them, right? What you probably would have done if you were really trying to show, for instance, that there are more numbers between, say, I don't know, 1 and 6 than 1 and 4, is you probably would have been like, okay, look, 1, 2, 3, 4, 5, 6. And then you've been like, look, 1, 2, 3, 4. Look at it. There's extra. But what you're doing when you write it like this is what you're doing is you're showing that there's no bijection, right? Yeah? You're showing that, hey, look, you can inject this one into that one, but you certainly cannot surject it. Yeah? Okay, so I guess what I'm trying to get at is that, hey, check it out. You finally have the ability to prove, I guess, relatively obvious facts about counting without having to wave your hands a lot. Yeah? Cool. All right. Well, let's talk about denumerable sets. Section 7.3. And this will be a fun one. We could go through it a little bit quickly at some points, since we've already seen a few things from it before. Denumerable sets. So I will start by throwing a quick definition at you. Let me throw a quick definition at you. I'm going to go slightly out of order with the first 2 items in your notes. I'm going to throw the definition before I prove the theorem. So here's the quick definition. Let A be any set. We say A is, and here are the following options. 1, denumerable if A is equinumerous with the naturals. 2, countable if A is finite or denumerable. And finally, if A is not countable, what might we call it? Uncountable. How about uncountable if A is not countable? Okay. Do you believe that there are any sets in the third category here? I would hope that you believe that there are sets in the first two. I would hope that you believe that there are finite sets, right? We've seen a few of them. And I would hope you believe that there are denumerable sets. The naturals are one example of them, right? But are there uncountable sets? Let's find out. Okay, so first off, in our journey to see if there are uncountable sets, which I claim is actually not very obvious of a fact, right? It doesn't, it seems kind of strange that there might be sets that are so big that you can't count them. It seems almost impossible, but it is the case. In our journey to see this, let's first start out by getting at some basic pieces that you might, if you were trying to build an uncountable set, what would you maybe do? Maybe you would try to take a lot of countable sets and somehow put them together, yeah? Do something like that? Okay, well, let me build up to a nice little fact that says that this is by itself not really enough. So let me show you a theorem here. All right. If A is an infinite set and B is a finite subset of A, then A without B is infinite. Okay, this perhaps seems relatively obvious. If you have endlessly many things, and then you get rid of a few of them, but not endlessly many of them, you still have endlessly many of them, right? Okay, well, let's show this. It's a relatively straightforward proof. For any subset B of any set, we have that A is indeed equal to B union A without B. Do you agree with that? Okay. That is, all of A is certainly equal to all of A that is not in B, and then also the part that is in B. Yeah? It's just everything. Okay, cool. All right, so suppose to the contrary that A without B is finite. Then A is the union of finite sets and is thus finite. A contradiction. Yeah? That is, if A without B is finite, then you have a finite set, union, a finite set, and that's all of A. Would you agree that that is finite as well? Perhaps there's a missing step in the full formality of it, which would be to explicitly show that the union of two finite sets is finite. We have effectively done so. It's not a terrible construction. All you really have to do, if you don't believe that, is the following trick, which is this. So suppose B and C are finite, then B is equinumerous with NN, and C is equinumerous with NM for some N and M in the naturals. Hence, if B intersects C is empty, B union C is equinumerous to N plus M. To see this, all you have to do is use the bijection here and the bijection here, and then just take one of them and shift it up. Yeah? Do you agree with that? Does that make some sense? So to see this, let f from b to n, and g from c to n, m be bijections, and define, let's call it h, from b union c to n plus m by, and I'm writing all around on the board right here for no terrifically good reason other than poor planning on my part. All I'll do is I'll do this. I'll go h of x is equal to, well, it's going to be pretty straightforward. I'll say f of x, if x is in B, and then I will go bigger than n, yeah? So I will go n plus g of x if x is in C. Cool with that? Yeah? Okay. Can you show that this is a bijection if f and g are? Totally. Here's the entire picture of what this is and what this is saying. All it's saying is the following. It's an easy picture to draw, actually. Here is B, here is C. This has some stuff. Here's N. N, here is N, M. This has like maybe like 1, 2, 3, and 1, 2, 3, 4. Maybe I have A, B, and C, D, E, F, and G. You've got some bijection taking things across over here. Okay, here's all you do. 4, 5, 6, and 7. Yeah? That's all you got to do. You just got to relabel one of them a little bit bigger. Yeah? Now, putting these guys together, hey, look, I have n plus m. See? That's all I'm doing. It's just lining it up. Does that make some sense? Okay. If you buy that, then good. We know that infinite sets have proper subsets that are also infinite. In fact, you could even use something like this to define an infinite set if you were so inclined. Notice that if you wanted to find finite subsets do not have this property. That is, any proper subset of a finite set is not equinumerous with the whole set, right? That is, if you take a proper subset of a finite set, it has strictly fewer things. If you take a proper subset of an infinite set, it is entirely possible to have just as many things. In fact, you always do. Yeah? Wild, crazy, kind of cool. All right, so what can we do with this? Well, maybe this is strange at first. Maybe you don't like it. So let's just jump back to thinking about, I don't know, I'm erasing this part. Maybe I'll erase the other board so we can point back to this one. Let's do a quick example, I suppose. One of the reasons you might want to do something like this is that perhaps you ask yourself, can I build an uncountable set just by putting a couple of countable sets together? Maybe like 2 of them's enough, right? Maybe, for instance, and you know this to not be the case since we've actually constructed a bijection, but perhaps you're like, maybe the rationals are uncountable. After all, it seems like there's kind of a lot of them, right? We saw the nice picture where you draw the squares before, and maybe if you've forgotten that, I can sketch it for you again momentarily. But this is one of the kinds of things that people thought about in the beginning. They said, maybe I could just take a couple of countable sets and sort of chain them together in some sort of a way to get you know, a bigger set than countable. But it turns out that this doesn't work. So before we get there, let's do this quick example just to make sure we understand what's going on. So the set, let's call it A, which is just 2k, such that k is in the natural numbers. This is just the set of even natural numbers, yeah? Just look at all the even ones. Okay. This set is denumerable, I claim. You agree that with this? i.e., A is equinumerous with the naturals. Yeah? To see this, define the function f from the naturals to A by f of n is equal to 2n. Yeah? This is certainly both an injection and a surjection. Is there any even number it doesn't hit? No. Does it hit every even number? Yeah. Just straight up from how we've written this. It's 2k for k a natural number. This thing sends a natural number to 2 times that natural number. It certainly hits all of the things there. Cool. Okay. Yet A is indeed a proper subset of the naturals. That is, it is a proper subset of n with the same cardinality as n itself, the same number of elements, yeah? And worse yet still, the naturals set minus A, which is just equal to 2k plus 1, such that k is in n, the odd integers, or the odd naturals, also has the same cardinality as all of the naturals. Whoa, a little bit wild, eh? Oh, so it's indeed entirely possible to have 2 proper subsets of the naturals, both of which are exactly the same size as the naturals. And when you put them together, you still just have the naturals. So in some sense, what this is saying is that were your idea to make an infinite set be something as simple as like, hey, could I take 2 copies of the naturals, 2 countable sets, or if it's not the naturals, then something that you can put in bijection with the naturals. Why do the bijection? Why not just use the naturals, right? Can I take a couple of copies of a countable set and somehow get an uncountable set? Here's an example where I have directly put together 2 countable sets, and I ended up with a countable set, right? So perhaps this won't work. Maybe we'll need something more complex than that. Maybe we'll have to appeal to something crazier. Maybe we'll have to use a different set. Maybe we'll have to, I don't know, keep it real, right? Use the real numbers. I don't know. We'll get there. But let's prove a couple of theorems that this would seem to suggest. Here's the first one. If A is denumerable and B is equinumerous with A, then B is denumerable. This would be a helpful little fact. The proof is easy. if A is denumerable, then what this means is that A is equinumerous with the naturals. Okay, so since this triple equal sign, this equinumerosity relation, is an equivalence relation, it is transitive, and B, which, if you notice, is equinumerous with A, is indeed equinumerous with N. So B is also denumerable. What do you think? That is, all you need is the fact that, hey, having the same number of things, if A has the same number of things as the naturals, i.e. is denumerable, and B has the same number of things as A, then B has the same number of things as the naturals. Yeah? Cool. Okay. So let's think about this theorem. If A is a subset of the naturals, then A is countable. Notice I can't say denumerable here because it's totally possible to have a finite subset, right? Okay. Proof. If A is finite, is countable. Okay, we're good there. Since countable, by definition, is either finite or denumerable, the finite case is easy. If A is not finite, let's show that it's denumerable. So in some sense, I guess what I'm getting to is that when we did this trick right here, and it didn't work to give us something that is uncountable, that is, if we take two chunks that are countable, you can't put them together to get something uncountable. Maybe your objection might be, perhaps you didn't pick the right chunks, right? Maybe you're like, well, the even numbers are the wrong ones to pick, or the odds are the wrong to pick. Maybe we should pick some other chunk of the naturals. And somehow if you put them together, you can get something bigger. But you can't. That's what we're going to show here. We're going to say, hey, look, if you've got a chunk of the naturals, it's countable. It's either finite or there are just as many things as the naturals themselves. Yeah? So in some sense, what we're trying to get to is a way of saying that, look, you have to get to bigger than countable via some other avenue other than just taking a couple of countable sets and putting them together. We're getting towards that. Okay, so if A is finite, it's countable. So suppose A is infinite. Infinite, not finite. Okay, here is the process. We define a function, f from the naturals to A, as follows. All right, here's the whole trick of it. A is a subset of the naturals. Does this mean that it has a least element? It does. Okay. Since A is contained in the naturals, A has a least element. So set f of 1 equal to this element and call it A1, let's say. Yeah? I.e., A1 is less than or equal to A for all A in A. Okay, cool. Now, what can we do to get the next element? Well, you could take the least element out of A and then send 2 to the next smallest one, right? Which is the smallest one of A without A1, yeah? So define f of n to be, I'll write it this way, I'll say the infimum, if you recall what this is going to be the infimum of a set minus a1 through a n minus 1. Where, to be clear, a1 through a n minus 1 are these minimal elements, yeah? So, jumping to the other board, now, we should write that quite clearly. Maybe even I can write it without a1 through a n minus 1 and just write it as f of 1 through f of n minus 1. Yeah? And you don't even need a1 there if you want. I should switch back boards. This is an unfortunate location for this. Wait, I can just actually move the camera? Oh my gosh, I can go between boards. This is crazy. I didn't realize I could do that. Hey, how about that? I can even zoom a little bit. Yeah, that's going to be way better if you're an online student. Cool. That is, so here's what I had before, just to be clear to everybody. So this is a1 through a n minus 1, where a I is equal to f I. Yeah? So here's the picture. You've got A right here. Maybe it's like 3, 9, 1, 1, 4, 2, 6, 1, 1, 4, 2, 7, and so on, right? Here's what you send 1 to. The first thing. 2, the next thing. 3, the next thing, right? So all we're doing is we're saying, hey, look, A is a subset of the naturals, so it has the least element. A set minus that least element is a subset of the naturals, so it has the least element. That is, we're always able to find the next smallest thing, and that's what we map our next value to. Cool, right? This is indeed a bijection. This is indeed a bijection. Since Fn is what? Strictly less than Fm for n less than m, yeah? And I guess to be clear, what I'm saying, this is precluding the possibility that f of n is equal to f of m for n not equal to m, and since what? We've got injectivity from that. Is everyone feeling good about injectivity there? Okay. Is anyone feeling weird about surjectivity? Okay. I'm going to say satisfies A is less than or equal to the subset of A given by you know, that. What I'm trying to say there is that every element is the least element amongst the elements larger than it, right? Kind of an obvious statement, yeah? So what this shows is that every element is eventually a least element, right? All you have to do is remove all of the larger elements. That is A, or even better than this. That is, A is less than or equal to B for all B and A set minus the things that are smaller, right? That is, every element is eventually a minimal element if you have removed enough of the things that are smaller. Cool. So it's indeed injective and surjective, hence it's a bijection. Hence, now we're done. There's a bijection between A and the naturals, so they are indeed equinumerous. Cool. Well, this throws a wrench into things. If we're trying to construct some uncountable sets, we'll have to try some more tricks next time. I'll see you then. Have a great day.